For decades, the standard cosmological model has assumed our universe is an isolated vacuum, expanding into absolute nothingness. This model creates several physical contradictions, specifically the horizon, flatness, and singularity problems, which remain unresolved by standard physics. These contradictions stem from the friction between the macroscopic rules of general relativity and the microscopic precision of quantum mechanics, prompting a search for a unified cosmological theory. A mathematically rigorous alternative has emerged to reconcile this friction: Schwarzschild cosmology, also known as the black hole universe model. The central thesis of this framework states that the observable universe is not an expanding bubble of isolated space, but the interior region of a supermassive black hole. Under this model, the black hole containing our universe exists within a larger, older parent universe. If this geometry is correct, the expansion of space is the internal evolution of a gravitationally bound system, enclosed by an event horizon. The evidence for this model relies on empirical data applied to the Schwarzschild metric, which defines the physical boundary of an event horizon. The Schwarzschild radius represents the exact spherical threshold, where the escape velocity of a massive object equals the speed of light. This threshold is defined by the equation Rs equals 2gm over c squared, where g is the gravitational constant and m is the mass contained within the volume. In standard cosmology, the primary metric for scale is the Hubble radius, representing the causal boundary of our universe's expansion. The Hubble radius is calculated as the speed of light, c, divided by the current rate of cosmic expansion, h0. To compare these two boundaries, we must calculate the exact mass of the observable cosmos. This requires the condition that the universe is spatially flat. This map shows the distribution of temperature fluctuations in the cosmic microwave background. The geometry of these fluctuations provides empirical proof that our universe is spatially flat. In a spatially flat universe, the actual density of all matter and energy matches a specific threshold known as the critical density. The critical density formula is 3 times the Hubble constant squared divided by 8 pi g. We calculate the total mass of the universe by multiplying this critical density by the volume of a sphere with a radius equal to the Hubble length. When we take this mass-energy content and plug it directly into the Schwarzschild equation for an event horizon, the gravitational constant and the complex fractions cancel out, leaving us with a final output of Rs equals c over h0. This reveals a mathematical identity. The Schwarzschild radius required to enclose the mass of our universe is nearly identical to the Hubble radius. Physicist Tianxi Zhang formalized this relationship as the law of space-time equivalence. It dictates that any region of space satisfying this specific mass-to-radius ratio necessarily constructs its own enclosed spacetime. This symmetry is often dismissed as a coincidence. However, the mathematics indicate the observable universe satisfies the exact physical parameters of a black hole interior. If bound inside a black hole, what force drives the observed acceleration of cosmic expansion? The standard model explains this acceleration by introducing an unobserved field called dark energy. The Schwarzschild alternative relies on a kinetic process, expansion driven by the continuous accretion of mass and radiation from the parent universe. The boundary of a black hole is dynamic, inhaling streams of matter and radiation from the space surrounding it. This process is governed by a law of space-time expansion, where the rate of increase in the universe's radius is proportional to the rate of mass inhalation. As material crosses the event horizon, the internal spatial radius must expand to maintain the required mass-to-radius ratio. Observed cosmic acceleration is a consequence of a feeding event horizon, making dark energy unnecessary. In the parent universe, a massive star implodes under its own gravity, collapsing inward against a dark cosmic backdrop. Standard relativity predicts this star will collapse into a point of infinite density, a singularity that breaks the laws of physics. To bypass this impossibility, physicists use a mathematical extension of relativity called Einstein-Cartan, or ECKS theory. ECKS theory eliminates the constraint of a symmetric connection. This allows spacetime to possess an inherent twist, known as torsion. This torsion accounts for the intrinsic angular momentum, the quantum spin of microscopic matter. Inside the collapsing star, this spin is generated by quarks and leptons, known as fermions. During the final fractions of a second of gravitational collapse, stellar material reaches an extreme density. At this limit, a coupling occurs between the quantum spin of the fermions and the macroscopic torsion of spacetime. This coupling generates a massive repulsive force, overwhelming the inward crush of gravity. The collapsing matter violently rebounds outward in a massive shockwave, completely preventing the formation of a singularity at the core. This big bounce initiates the internal expansion of the new black hole, birthing our observable universe. The black hole universe model functions across two scales: the microscopic torsion bounce at its origin and macroscopic mass accretion driving current expansion. By combining these mechanisms, the model unifies the quantum spin dynamics of EKKS theory with the large-scale gravitational geometry of general relativity. This unification addresses the three core enigmas: the horizon problem, the flatness problem, and the singularity problem. Torsion prevents the singularity, the Schwarzschild identity enforces spatial flatness, and the pre-bounce state of the parent star ensures all matter was in causal contact, solving the horizon problem. Every mechanism in this model, from the measurement of critical density to the repulsive force of fermion spin, is grounded in established physics. This alignment demonstrates the mathematical symmetry between the scale of our universe and its event horizon limit. Following the math to its logical endpoint leads to a view of the cosmos not as an infinite void, but as an evolving gravitational entity nested within a larger cosmic architecture.